Hey folks, welcome back to the Geometry Nodes game. In this session, we're going to be having a look at how we can build a terrain system, how we can collide with said terrain, and then how we can also collide with things like buildings and other structures in our scene. All kind of smoke and mirrors, but it just gives you some flexibility to play around with this in a way that you want. Do a little bit of world building. It's all Blender. This is your place to play. So let's go ahead and jump in here. So far we have our vehicle, and if we monitor the controller and I play the timeline, you can see that we have steering, we can drive, we can keep driving, we can brake, we can reverse, and everything like the wheels rotating and steering, this is all working perfectly. So the next real thing is just to put it down on the terrain. But first of all, we need terrain. The way that you want to build your terrain is totally up to you. The way that we're going to design the vehicle to interact with the terrain makes it super flexible. So you can have a sculpted terrain, although maybe the resolution will be too high. So if you do something like that where you have an extremely high mesh density, then just throw a decimate modifier on it, crunch it down, and then you've got one that you can look at, and the version that you've applied a decimate modifier to, you can use that as your collision version. We're actually going to be building a sort of LOD system. So in our game objects collection up here, let's go ahead, press C, bring up a new collection. I'll call this one Colliders. And inside here, I'm going to do another collection called Terrain. In my terrain collection, I'm going to add a new object, just a plane, which I will call Ground. Now you can add as many different objects as you want into this collection. I'm just going to do it with the one here and that'll be fine. So let's create a new modifier, period, because I don't need to use this multiple times. This one is going to be called ground. Let's get rid of that group input. So what I'm interested in doing here really is creating an LOD system where I have high resolution terrain around my vehicle and low resolution terrain away from the vehicle. And because I'm going to be doing a procedural displacement, I don't have to worry too much about the resolution because the mesh and the displacement are separate. Now you could also do this if you were using a height map or some other method of creating the surface, but this is how I'm going to roll with this. So first of all, mesh, primitive, grid. Let's add this. I'm going to make this a kilometer, so 1,000 meters square. How big do I want my tiles? If I go 100 by 100, and let's just turn on, let's go wireframe. Here we go. So you can see that our vehicle is actually massive. And if you look at the detailing on it, it is actually huge. It's got ladders and things. So it is quite a large truck, this, much larger than a regular vehicle. But as you can see, 10 meters square is actually fairly small here. Maybe let's reduce this down to somewhere, maybe 21. There we go. These tiles are a much better size. And the reason we went for 21 across 1,000 meters is because it makes the next part much easier. In fact, let me set it back to 20 and you'll see. If we now instance on points, another grid, and 1,000 divided by 20 gives us 50, so 50 in both of these, you can see that we have a bit of space around each one. And this is because we should actually have that 21 points. And it's just because if this is let's say this is 2 meters. So we have 0, 1, and 2. Then we actually have 1, 2, 3 points making it up. So for that even spacing, you want 1 in addition. All right, so that's fairly simple stuff. Let's look at the mesh density now. So if I have 50 meter square and I'm going for a 20 vertices, it really just depends how fine you want your mesh around the vehicle. For example, I could set this to 50 and then I've got almost a meter square on my terrain. But as you can see, this is going to be a very heavy mesh. I'm going to go maybe 25, so approximately 2 meters. But you can see if I have a whole kilometer of this, it's going to be very heavy for us to work with. If I go ahead and just realize these instances, I have 250,000 points, which is quite a lot of points, 1 million triangles. Sampling this kind of terrain, raycasting at it, doing everything that we need to do to get that game feeling, this is not viable. So what we're going to do, let's copy off this grid and we're going to do another one, same size, but we're going to reduce the mesh density. Maybe we go down to 10. And then we're going to do another one where we reduce it even further, maybe down to 5. In fact, maybe I'll go 25, 15, 5, and then 2. So I'll have 4 of these grids. And there's a node in Geometry Nodes called Geometry to Instance. And we're just going to plug these in order from highest density to lowest density. Remember, this multi-input socket is ordered, so it needs to come in the order that we've made them here. Plug this up into your instance, select pick instance, and now you can see. Okay, fantastic. We've got some kind of repeating pattern. This is not exactly what we're after. What we want is to take the game manager into our node graph here, set this to relative. This geometry is going to come through as splines if we look at our spreadsheet down here. So let's grab a curve to mesh to turn this into a mesh. And then we're going to do a geometry proximity to find how far away from the edges we are at any point. Then what we can do, just bring this down to the bottom, we're going to take our distance through a map range. And this is going to go into our instance index. Let's say maybe 5 meters away from our object, up to 100 meters. Is that fair enough? And then our max wants to be a bit higher. So can't go above 4 here, but we can go up to 3 there. So we have 0, 1, 2, and 3, so we'll go up to 3. So everything over 100 is going to be the lowest resolution. Let's just show that wireframe. And everything super up close is going to be higher resolutions. Now you can see I might have gone a little bit too far with that. Something like this might be better. So it's just sort of approximately halving each time. And then all we need to do is we're realizing, see now we've only got 10,000 rather than 250,000. And then we can come in here and just do a bit of displacement. So let's grab a geometry, right set position. And then we are going to do something very simple here, just offset with a combine XYZ. And we're going to take a noise texture, which I will turn off normalize. So this is a new function inside Blender in 4.0, I believe, and above. And this basically says normalize to the 0 to 1 range. So this is the default behavior. If you turn this off, then it kind of averages around 0 instead of 0.5. So that's nice to have. And we're going to just take this factor through a multiply, plug that into the z-axis, and then we're going to reduce our scale somewhat. Let's go down to 0.005 maybe. Increase this multiply and see where it takes us for a terrain here. Nice. Maybe a bit more roughness. Let's turn off the grid there. We'll also turn off the world floor. And we might want to set shade smooth on here as well. So you can see that we're getting gaps in between our land tiles, and that is to be expected when changing resolution in this way. So this is not really how a game would deal with LODing terrain and having sort of a variable resolution. But you can always make sure that you've got things aligning count-wise. So maybe I set this to 30, 30 or 31, 31. Which would then go to 16, 16, 7.5, so that's about 8. And then we've got 5 for these ones. And that's going to seam it up a little bit better, just so that you're kind of trying to align those grids a little bit better. Oh, maybe these should be 9 actually. And 17. 33 will do on there. There we go, that's a bit better. A little bit cleaner. Obviously we're still having gaps in the edges here, but I'm happy to leave it as is. We can always push out this section a little bit further. So that maybe we're going from 100 to 300 is our fall off area. Something like this. Let's try and bring that down a little bit. And I might extend that a little bit. In fact, maybe just starting at 0 works quite well there. Okay, fantastic. That's looking great. Let's just apply a material on here. So let's set material, and we'll just make sure that we have something nice to look at on the floor. So create a new shader, create a new material. This one is going to be called ground, which I will now select, for my ground. And I'm just going to do something simple with a checker texture. And I want this to be based on the world XY, so just a 2D coordinate space. So let's take a texture coordinate node. We'll take object coordinates through a multiply, just to make this only in the XY space, so multiply it by 110. And that's already a lot better. And then we can reduce this scale. Somewhere like this should look pretty good, I think. It just gives us a little bit of variation. I'm going to make it all quite dark as well. Just give us a bit of a checker. Nice. Might also increase the roughness for the terrain. Fantastic. Okay, so this is going to be our terrain object. Let's get rid of that shader graph. How do we now handle the collisions? Because if I press play, nothing happens. Let's go back to our game manager. And to begin with, I'm going to actually increase the Z position. So I'll return to the beginning with shift left arrow. And we're just going to move our vehicle up a little bit here. Not crazy far, but just so it's above the terrain. Let's come across here before we do the solving of the spacing or the wheel rotation. Let's just move things along. And in between movement and spacing, we're going to make a new node group. Control G on that reroute, tab out. This one's going to be period solve underscore ground. Right click, show hide, node options, tab in, get rid of that reroute. And this is our chassis and chassis coming through. So how do we want to use this? Well, when we're above the ground, we want to raycast down to it. So let's add right set position. And we're going to be moving down towards the surface. Let's also add a geometry sample raycast. And to this, we can import our terrain collection. So we have our terrain collection, set this to relative, and we will realize the instances so that we can use it with this raycast. Now, in what direction do we want to be raycasting? Straight down, maybe, but not actually quite right. So if I have a vertical thing, and here's my space that I want to bring down into the contact with the ground. If I go straight down, that's fine. We'll get this. However, what happens if we have a slope like this? Well, if I contact that slope here, you can see that we're cutting through. So what I actually want to do is I always want to raycast in the direction of the nearest surface point. Fortunately, this is very easy for us to do. We take the realize instances node, we take a geometry proximity, and we're looking for the nearest point on the faces, which is this position here. Then to get the direction towards that point, I just need to compare it against my current position. I always forget how to do this, which way it is. Let's say I'm trying to get from 1 to 3 in this direction. I know that this is +2. So if I do 1, subtract 3, I end up with -1. And if I do 3, subtract 1, I end up with +2. So it's the target, which is the surface position, subtract the current position. People always ask me how to get good at maths, and frankly, I'm not. I just do a lot of things like this to help me out. Got to find the ways to help yourself out. So there we go. That is our direction to the surface. Now we have a ray length, and this is going to be defined by something. And we have this position here. So there we go. Cool. Almost. But not quite. Something is going wrong. So every frame we point towards the nearest point on the surface, fix the trailer spacing, and we end up with this problem. So it's working, but it's not quite working. So let's think about how we want to actually use this. When we're solving collisions like this, we only want to be solving the collision when there is a collision. Can't be solving our distance to everything all the time. It's going to be really heavy, and it's also not useful. You know, if my wheel is here and the ground is here, I don't need to solve this. I'm just doing a jump. That's totally fine. That's legal. So one of the great things about raycast is that we can set the ray length so that we're not searching beyond where we need to. And when we do hit something, we can know because it's going to tell us with the is hit. So first of all, let's work out how far we actually want the ray length to go. And in this case, it's going to be a combination of the wheel radius named attribute and the suspension travel. So if we think about where we want the wheels to actually be on our vehicle, if this is the central position of the axle, then we have a certain amount of travel that we want to have, and then we also have the radius of the wheel bringing us down to here, and this is where the ground is going to be. So let's just join these two together, and we're now adding wheel radius and suspension travel. These together are the rail length. So if we haven't hit the ground within that distance, then we are falling. And this is something that we need to know. So let's make sure that we have a store named attribute up here. This is going to be called ground_contact. And it is going to be a Boolean on the point domain. So of our chassis needs to know whether or not it has hit the ground. This is just going to read the is hit. The next thing that we're going to be using is going to be the ground normal. And we're going to use this for a bunch of stuff. We use it for making sure that the wheels are positioned correctly. We use it to make sure that the angle that we've actually instanced our cab and our trailers matches the ground, so everything kind of follows through nicely. This is going to be a vector on the point domain, and it is going to be the hit normal like this. But we only actually want to write this if we've hit the ground. So up until the point that we hit the ground again, it will use the previous version. So it's just going to stay fixed until we hit the ground again. So it's a really nice way of working. Do love a raycast during a loop. Gives us a lot of information. Okay, so before we go any further, let's throw these nodes into a group because we're going to need them a couple of times. And actually the rail length will stay on the outside. So Control G, tab back out. This group is going to be called sample_ground without a period because we're going to need it multiple times. Just hide those node options there. And here we go. So I'm going to be adding a few more bits in here. First of all, the terrain collection comes in the front. I will also just remove the name for that just so it goes there. And we'll set the rail length. This is then the terrain. Fantastic. Now, what are we actually doing here? Well, I want to know a few bits of information. First of all, how far do we want to correct by? What is our offset distance? Is the offset distance that we want to achieve, so where the chassis ends up above the ground, is this offset distance the same as the rail length? With the chassis, yes. With the wheel suspension, no. Because when we do the wheel suspension, we're going to want to have a rail length of the suspension plus the wheel radius, and we want the offset radius to just be the wheel radius. There's a distance discrepancy there when we do suspension. So for this, we're going to keep these separate. So let's grab another group input. I'm going to add new input, float, subtype, distance, and it's going to be called offset distance. And then we're also going to add another one for epsilon, and I will tell you about that in just a moment. Epsilon. And again, a distance. I want to know the direction that I want to do the correction. So if I have a wheel that is through the ground, and I have my hit position, and I have my original position, the direction I want this to go is straight back towards itself by the difference of this overlap. And the difference is the difference between the hit distance and the wheel's radius. Or actually, in this case, the offset distance is what I should say. So let's put this together. The direction is quite simple. I'm going to take the position, subtract the hit position, and let's just, we'll keep this down below. This gives us the vector coming back towards ourselves at the bottom here. I want to normalize it to give me the direction of that, and then I can scale it to a new size. What is the new size? Well, it's going to be the difference between the offset distance, which is essentially the radius of this circle, and the hit distance. That'll return this remainder piece down here. So let's take our offset distance, subtract the hit distance, and we're crossing these so the offset distance goes in first because it's going to be bigger. And then because when we're dealing with float, numbers, floating point numbers, if I have a circle perfectly on a surface like this, my hit distance is exactly the same as my ray length. And when those two things are exactly the same, if they're exactly both 1 meter, floating point precision errors means that I can't guarantee that it will register a hit, because one might be 0.99999, the other one might be 1.0001. So there might be a very slight discrepancy there. Just to guarantee that things work out, rather than moving it up all of the way, I'm just going to correct it by slightly less with this epsilon value here. Because we're dealing with terrain and tires as well, you can actually go for quite a high epsilon and it'll just feel like it's sunk a little bit into the ground. All right, so then this can just go up into this scale. This can be passed out here as the offset vector. And then let's save this, and we're going to plumb this over into the offset of our set position. And there we go, these are looking pretty good. Now, for this first one, where we're dealing with the actual position of the ground collision against our chassis, we can just put the ray length and the offset distance as the same. And our epsilon can be something like 0.1 meter. If I now press play, what is actually happening here? Well, we do hit the ground, and it actually works pretty well. So there's a few things that we're going to want to make as tweaks here. So first of all, we want to solve the ground problem, because right now, if I accelerate, we're Santa Claus with the sleigh. We're just flying through the air. So I want to make sure that my movement is tempered slightly by whether or not our ground contact has happened. So let's come back into our solve movement. And just at the end here, just let's make sure that we've got these rerouted just so that I've got something to work with. After our scale, we're going to add a utility switch node. This is going to be the vector, and only when true are we going to use this scale value. And it's going to be based on the Boolean ground underscore contact, which is a Boolean. Here we go. So only when true do we want to use this. So if I press play and I hold the trigger, there we go. It's waiting until it hits the ground completely. So that's great. However, we don't just want it to actually be stationary when falling. Now, the rest of the time, we're going to set this to 0 right now. But if I press play, we can see that clearly it's falling. Why is this? How can we fix it? Right now, movement should be set to 0. Go back into our solve ground, into the sample ground, and just after this scale here, let's grab another switch, set this to vector, and I'll drop it on here. So use this if true, when is hit, just bring that along on a reroute, and otherwise 0. So now when I press play, you can see that we no longer fall. If I mute this, we start falling again. So all of our falling, although it's easy to look at it and think, oh, well, that's convenient that just works, we actually want to make sure that it's coming through our movement in the solve movement here. What we actually want to have happen is every update, we want to take the existing move, which is the offset that we're making each frame. We want to take the move of the previous frame if we have no ground contact. So we want to continue our movement. However, if there's no ground contact, it means that we're falling. So we also want to subtract a little bit from the Z, or add a negative Z. So let's grab a vector math node on here. And just to the Z, I'm going to press play. Let's have a look at what we need. That's probably too fast. Let's go minus 0.03 maybe. That might be a bit too slow. Let's go 0.05 in the negative. There we go. And that's just falling quite conveniently down to the ground there. Nice. That's working. Fantastic. Okay. So the ground is solved. Let's monitor the controller. And let me show you something. So if I drop to the ground and then I accelerate, it does start fairly well, but it definitely accelerates from nothing. If I go to the start and I hold accelerate, and then I press play, it goes very abruptly. So it's quite subtle, but it is happening. And the reason is, we come back to here, the current speed when we are falling from stationary, the current speed is just the length of the movement. So as we fall faster and faster and faster, our initial acceleration, like the movement forwards of our vehicle, is based on that falling speed. And that's actually not what we want. So we can do one more thing in here just to even this out. And this is another store named attribute node. This one is going to be called move_contact. And this one is only updated when there is ground contact. So it's just the same movement. But rather than updating every frame, which we do need one of these to do because of our falling vector needs to increase, we need to accelerate down. We need this one to only update when there is ground contact. And then, back on our current speed, if we look for move contact instead, then this will only be updated for our forward acceleration, for our driving around when we are driving around. So if I now monitor the controller, hold the trigger down and I press play, there we go. You can see that we don't start accelerating until we actually get wheels on the ground. Fantastic. So when we were doing our ground collisions, we also stored the ground's normal at each point, and we need to use this in a few places. Just before we move on to solving our wheel position, we're going to make sure that we've solved the roll of everything, because there's 3 places that we're going to need to actually solve for the ground normal. Jump into your vehicle. In the body node group, we have an align Euler to vector. If I just unmute this, you can see that things are going to rotate around like so. Now, instead of just using a vector, I'm going to use a named attribute node. We are looking for the ground normal, and this goes in here. So you can see before and after, this is now following the ground a lot better. You will notice, however, that the wheels are now clipping through on this low side. And to solve this, we need to go back to our game manager, go across to your solve suspension. And rather than using the cross product here, we're going to use the ground normal instead. So again, ground underscore normal vector. And that's going to fix that up. Now we can't actually use this all the time because it hasn't necessarily been sampled to begin with. You know, if I go back to the first frame, the wheels get sucked inside because until we actually touch the ground, that ground normal is just 0, 0, 0. So if the length of ground normal is equal to 0, then what we will do is we will use a switch node, set to vector. So if it is equal to 0, we will set it to 0, 0, 1. So it's just an up-down vector. And there we go. Great. That's working nicely. The last thing that we're going to need to do here, go back to our vehicle one more time, find the wheels group, and just before we do our rotate Euler for the wheel rotation, we're just the same as before. We're going to do a Z pivot on the y-axis because we've already found that with the wheel direction. And our named attribute here is also going to be ground normal. There we go. Just to make everything follow the ground properly. We just needed to do those 3 things. And now we can actually solve the suspension offset. So why are we solving suspension offset? Well, because as you can see, our wheels don't touch the ground. Obviously not ideal. Again, back to the game manager, look in your solve suspension setup. And just before we do our delete geometry, so in this space in the middle, we are going to be using that sample terrain group. So let's add a new group, the sample ground. And if we look at our group inputs here, we see that we've only got a few, and this is because we've hidden so many of them with that period prefix. So that's one of the nice things. I'm going to show hide node options. There we go. And we are going to be sampling the terrain. So let's just go ahead and grab a geometry right set position. We're going to be using the offset vector as our offset vector. And as you can see, this has just gone straight down to the ground. The offset distance in this case is going to be the named attribute, wheel radius as the offset. There we go. And I also just want to make sure that I have an epsilon just to bring these slightly through the ground. So 0.1 should be fine in there like that. Okay, so this is going to feel a bit better. Now, if I go back to the beginning, you can see that 100 meters for the ray length is a bit too long. So I could do this, the wheel radius plus the suspension offset. So I could add the suspension travel to this as my ray length. And then you can see that this has come down a little bit nicer. There we go. Just like that. Okay, let's have a quick test drive and see if there's anything that we want to change before we move on to general collisions. So let's make sure that we're monitoring our controller. And I want to just go over areas where there is changes of normal. That's what I'm really most interested in here. It is creeping a bit, look at that. So you can see it's sort of stepping between these different normal areas in a way which we don't quite like. I want to make sure that there's not quite so much of a problem with, oh yeah, you really see over the top there with this change of normal. Just things popping around. So how can we do this? Well, a very simple way. If you think back to when we did rolling resistance and we used that mix, we're actually going to use the same trick here. So let's go into our solve ground node group. Rather than taking the ground normal directly, what we're going to do is we're going to take a named attribute node for the ground normal vector, and we're simply going to mix from the previous one to the current updated version, and this is going to be the new ground normal. So if I have my factor set to 0, then it's just going to fix that terrain. So you can see there, this is not really what we want, but if I increase this factor, then it starts to move towards that, that new ground normal. So if I have this super, super low, like 0.1, then it should actually really improve the twitching. Will still happen a little bit, but because it's no longer sampling 100% of that, it's almost like it has a bit of a soft fall off on it. So now it's going to take approximately 10 frames to update all the way. And because it's changing every frame, it's essentially just lagging behind a little bit with the normal updates. So we can solve some of that flickering. Equally, you could do the same with the offset if you wanted to, and it would have a little bit of a rubber band look, but it would at least improve the juddering of different parts of your vehicle. Next thing to do is going to be generic collisions with other objects like buildings. In your game objects, colliders, let's add a new collection, which we will call environment props. Maybe that's a good enough name. And I'm just going to add some cubes, but these could be any number of things for you. So the reason I'm doing it with cubes is just because it's very low density geometry. And if you play games and you look at the collision meshes are often very low resolution meshes. So I'd recommend that if you're doing anything with collisions, if you have, for example, a house, then you actually create a little low resolution proxy mesh for it that is going to serve as the collider. Here we go. So just a few little buildings at random angles, and really they're just cubes, but that'll do for us. Go back into your game manager, and just after the solve ground, we are also going to make sure we're saving. Create a new node group in here, tab back out. This one is going to be called period solve underscore collisions. Now these are not self collisions. We're not going to be dealing with the truck driving through its own trailers. We're only going to be dealing with environment crashes like this. So let's come into here, grab that chassis into the both sockets. And this is actually very similar to how we deal with the ground collisions. So really much of a muchness. Let's bring our environment prop collection into this node tree. We're going to set it to relative. We're going to realize the instances, and we're going to pass this through a raycast. Just the same as before, we're also going to be looking at the surface. So we want to use a proximity node where we're looking at the faces, and we're going to simply subtract from the target position here, our current position, and that's going to give us the ray direction. So the ray length is going to be our collision detection distance, and let's just put this onto a value for now. So let's say maybe 5 meters. And let's see how we want to actually work with this now. So in this case, we're not going to be doing anything with the move attribute. We're just going to be simply correcting the position. So let's use a set position node in here. And this is really just because updating that move, although it would be more accurate, and we could do some things like bouncing off surfaces, but ultimately the performance drop from doing those additional calculations and storing things on the mesh is not worth the fidelity increase. It doesn't make it significantly different. So in this case, what we want to do is actually a little bit of magic. So if we are, let's take a surface. So let's say that we have a cube here, and let's do 2 different situations. So one of them, by the time we sample it, because we're driving quite quickly, we are inside. In this case, I do not want to move in this direction. I want to move in this direction. I want to move all the way out. Whereas if I'm just on the outside, then I only want to move that little bit back to the edge. So let's work out how we can do this. So in this case, we're actually going to use the ray direction. And we're using this because this is always going to be pointing towards the surface. Now I need to do a little check. If the hit normal is equal to in direction, the same direction as the ray direction, what does this mean? So let's say we have a surface, we have raycast at it, and the normal of this surface is in a similar direction. So it is at the same angle with an epsilon of pi by 2, meaning up to 90 degrees. So anything up to 90 degrees, this will say is equal. So this means that I am inside. So if this is true, I am inside the mesh. If I'm inside the mesh, then what I want to know is how to get out of it. So remember those 2 situations? We have one where we want to move the ray length plus the hit distance. And we also have one where we just want to move the ray length, subtract the hit distance to give us this little piece. So we've got the hit distance here. Let's add this to our ray length. And in another situation, we want to do our subtraction here. So in one we add, in the other we subtract. I'm going to switch between these based on whether this compare value is true or false. So basically, if this is true, it means I am inside the mesh. And if I'm inside, then I actually want to be using the add version, which uses both of these. Whereas if I am outside, then I want to just use the smaller version, the subtract. Then what I can do is, because I want to move in the direction of the ray direction here. So we're going to take this vector once again, put it through another reroute just so I've got that neatness. And we're now going to scale it by this switch. Now, before we do this, I just need to make sure this is normalized. So let's also just grab a normalize, because otherwise we don't know that that is a vector length of 1. In fact, it very likely isn't. Let's see if we need to change the data that we've gone with here. Now, this is one of those things where you could check it on paper, or you could see what happens when you drive into something. Okay, seems very happy for me to just drive straight through it. Let's take the scale. We're going to plug this into our offset. And we can see that this is not working exactly how we wanted, but not terrible. So when we play, it gets sucked over to the surface. So let's make sure that we've just got this selection on the set position when this is true. So let's play again. Make sure that we're using our controller, and I'm just going to drive over towards this building, and let's see what happens when we get close. So it's going to start pulling in. So rather than that, I just need to make sure that I am scaling this by -1. So I'm just going to multiply by -1. There we go. And let's try this one again. So now as I get close here, we can easily drive away, but I can't drive through. Let's try and crash into this. There we go. This one as well. Crash into it there. So 5 meters is a little bit big, so I'll probably go something like 3. But I'm also going to put this inside a node group here. So let's grab our controls, tab into this. We're going to add a new output at the bottom here. New output called collision distance. And it's going to be of subtype distance with a default of 5 and a minimum of 0. In this case, we're actually going to use 3 for this distance. And then we're going to just plug that in there. So the reason that I'm setting it with this control group, even though we then have to go in to modify it, is just because it means that we can now modify this from anywhere that we want to, versus rather than having to actually come into this node group necessarily every time that we want to. So that's how we can set up very simple collisions with objects in the world, just to prevent ourselves actually going through them. Now, if you are driving fast enough, you will still go through, just because the raycast potentially will not actually catch you when you are within 3 meters of the surface. If you're driving very quickly, you can still go through things. Equally, if you fall quickly, you can fall through the terrain. So just a little warning for you there. So that is us all done now for the fundamental driving system with geometry nodes. However, there's still a few things that we can do to actually make this into a game. First of all, we're going to be setting up a scoring system. So collectibles, things that you can go around and pick up as you're driving. And in the final video, we will be setting up the camera and the UI. So join me for those.